Thanks everyone for coming to hear my talk. This is not going to be very theoretical. It's going to be very practical, a lot of numbers and not a lot of funny Greek letters. So I'm Jim, and I'm actually a professor at EPITA in Paris, which is a small engineering school. I'm a career Lisper turned professor, and I've been working with Scala for just a year and a half or so. The presentation I'm going to talk about is fold, and we're very fortunate to have David here, who is the inventor of fold, as far as my research can determine. So thanks to him for making my presentation possible. We're going to look at actually what it is, in case anybody is not doesn't intimately know, and in particular my interpretation of what the function is. And we're going to look at three examples. The first two are quite practical and perhaps fun, and the second one, or the third one, is more abstract. So what is fold? So fold is a function that appears in lots of programming languages now, not just functional programming languages, but is used for extending binary functions to in-array functions. For example, if you know how to add two numbers, in mathematics you have this large sigma symbol for adding up a bunch of numbers, and fold takes the plus operation, the set of numbers you want to add, maybe it's ordered, maybe it's unordered, and some zero element. And likewise for matrix multiplication, if you can multiply two matrices, then via fold you can multiply any number as long as you have an identity matrix. Set union works the same way. We're going to look at logical conjunction. So if you have two Boolean functions and you want to find the intersection or the union of those functions, we have to write the function for two objects, and we can use fold to extend it to multiple objects. Typically, fold is implemented, at least in Common Lisp and in Scala, as two variants, a fold left and fold right. The semantics, or the final answer you get, is exactly the same, but where the parentheses are drawn is different. Usually that doesn't matter so much, but there are cases when it does, and so you have a couple of variants of the function. I want to look at one which I call tree fold. And the tree fold, basically we're going to pair in parentheses neighboring pairs, and then we're going to group pairs of pairs, and then we're going to group pairs of pairs of pairs, etc. And you always have a few left over at the end that you have to handle in some ugly way. Did I skip something? No. Let's look at the example of rational arithmetic. We want to add fractions. We want to add from left to right, 1 over 23 down to 1 over 67. I've chosen these so that they're hard. They're all relatively prime. So when we add the first two, that's pretty easy. We get a 2-digit number over a 3-digit number. When we add the next, we get now a 4-digit number over 5 digits. The time to add fractions is roughly a function of the length of the digits, more or less. So the longer the numerator and denominator become, the harder it is to add these. So one assumption that the fold implementation usually makes is that the operation is constant time. And in our case, the operation becomes more difficult as the computation proceeds. So we see that pretty much 1/3 of the way down through this computation is already become hard, and we're suffering from that. So can we mitigate that situation somehow? One way to do that would be to pair off everything and add the pairs together, and then you have a sequence which is half as big as the previous one, and you've already done half your work. It's not such a bad idea. We see that we sort of delay the hard computation to the end. This has a disadvantage that it doesn't work lazy anymore, which might not be a problem, but you have to consume the whole sequence before you can go on to step 2. Maybe it works, maybe it doesn't. What I want to suggest is a slightly different order of operation with the same grouping. So I want to start with is this right or left? This is left. I don't know my right from left. Start with the leftmost leaf level pair and add those. And then continue to the leftmost leaf level and add those. And now we have these intermediate values which we can add. But we can't do anything with the intermediate value that we've computed so far. So we go on to the next most left level, leftmost, and continue and continue. And now we have those intermediate values which we can add. And so the values that we compute sort of bubble up into a tree. The computation looks something like this. We need one mechanism that's perusing the list, feeding these values into a tree, and then once these intermediate values become available, it knows when to consume them, and then the next pairs go into the tree and they consume, and as it bubbles up, we finally have to have some ugly code at the end which just does everything else. But it's not going to be many. It's going to be less than log n of the number of elements because the tree's height is only log n anyway. So how we do the last couple, I'm not concerned about. There's a little bit of Scala code which handles that, and basically you have some code that consumes the list, handles off to this dwindle tree function which interacts until it's all finished, and then you have a reduce at the end which just slops up the rest. This example gives very good results that somewhat mislead us on how good this method is. So what I have here is adding up some consecutively more and more fractions up to 100,000 fractions. And 100,000 fractions with the normal fold left takes something like 80,000 milliseconds, 80 seconds. And then adding it with the tree fold and the pairwise fold, they both do about the same, come in at about 80 seconds. Many orders of magnitude faster, okay, for this particular type of computation. So does this approach scale to other types of problems? The next problem I want to look at is a classic problem in graph theory, the four coloring problem. So given a map, in this case they've colored the map with 11 colors, which is quite pretty, but you don't really need 11. You can actually color any reasonable map with 4 crayons. And I have a box of 6 because I couldn't find a box of 4. But you don't need the other 2. What you want to do is you want to convert the map to a graph and then color the vertices. So here we have a map of Europe, and we see Poland here with its many, many neighbors, and I hope that my map is correct. And you want to assign colors to all of the vertices so that no 2 neighbors have the same color. How do we do that? How do we determine the colors? So we know that we can do this in 4 colors because of a previous result. So we can assign 2 variables to every country, and then 2 variables are enough to distinguish 4 colors. For example, for France, if we assign A sub France and B sub France, and Spain, A sub Spain, B sub Spain, then we can construct a constraint that says the A's of France have to be different than the A's of Spain, or the B's of France have to be different than the B's of Spain, because if they're all the same, then they're the same color. So that's how we get a constraint. And then if we generate a Boolean function using fold, iteratively adding the constraints, and at the end we have a Boolean function that we need to satisfy. So the SAT problem is a notoriously difficult problem to solve, but we have a deceptively easy way of doing that. It does the Fields medal, though. We're going to use BDDs. So what is a BDD? BDD is a data structure, a very handy data structure used for representing Boolean functions. It has nice features. It gives us a canonical representation, so it doesn't depend on the syntax of the equation, it just depends on its truth table. And it's a very compressed form. Do we have any German speakers here? Okay, so somebody might, oh good. So you might challenge my interpretation of this. But in Germany, there's a mythical animal called the eierlegende Wollmilchsau. And this is an animal that lays eggs like a hen, gives milk like a cow, gives bacon like a sheep, like a pig, and gives wool like a sheep. So it does everything. And so I consider the BDD the eierlegende Wollmilchsau of Boolean algebra. There's all sorts of surprising features of this data structure. The one we're interested in are the fact that we can implement a Boolean algebra very succinctly, just a few lines of code, and that SAT solving now becomes linear time. You can challenge me on that later, because it's not exactly true, but I hope that you believe that. Given two BDDs, we can compute the and, the or, the and not of these in a very concise algorithmic way and come up with the resulting BDD. And given a BDD for a Boolean formula, we can solve the SAT problem simply by tracing from the root to any true node, which can be done in n steps. Computing the BDD is hard, and that's why I don't get the Fields Medal for this discovery. So back to the coloring problem. We want to color the map by coloring the associated graph. And the way we do this is we iterate over all of the borders. For each border, we compute a constraint. We merge these together with fold. This is an equation of 80 variables for 40 countries, and then we need to satisfy that Boolean equation. Okay? This is a graph of the performance that we see in terms of memory computation. The green line here is the fold left. So as the computation goes up to, and on my computer I couldn't actually solve all 40. I need a bigger computer. The memory allocation grows and grows and grows and grows and grows and grows because the constraints keep adding and keep adding and keep adding. But if we use the fold tree approach, then we see in some places we get a lot of memory consumptions, in some places we don't. So we leave the memory free as possible until we really need it at the end to do the final crunch, putting everything together. And the performance, we see that we don't get as good a performance difference as before, but the green arrow here is the fold left. It calculates the colored map in about 23 seconds, and then the tree fold calculates the same thing in about 18, 15 seconds. So it's good, but it's not as good as we were before. The final example, how many minutes do I have? Oh, that's too much. And this is the original problem that I started looking at when I was considering this algorithm. I want to generate randomly selected BDDs, potentially for some type of quick check, or in my case, I was just generating statistics about how much memory you actually probably need to store such a BDD. So to generate a random BDD, we need to generate a random truth table. This basically means for each of the min terms that represent the words of the truth table, we need to select some subset of those with some sort of distribution. Each min term is the same except it has the same literals, x1, x2, x3, x4, with some of them negated and some of them not negated. So choose some some yeses and nos to distribute across these min terms, and then use fold to OR them all together. Unfortunately, in this case, all three algorithms perform almost the same. So this was a bit of a disappointment, except at the very end when the memory starts really filling up. The fold left seems to be worse performing on memory full situations than the other, but the results are sort of dubious. So I wouldn't really trust these types of results. But what I asked myself is, are randomly selected truth tables really representative of the types of problems that you're going to encounter when you're using Boolean algebra? And I suppose that they're not. That Boolean equations that describe real events are biased toward the problem that you're looking at. So I reran the experiment using a concept that I call density. So the density of a min term is the number of truths as opposed to falses in the min term. So I reran the experiment with just using a density of 4 for 30 Boolean variables, and we see that the fold left is actually slower usually than the other two. The next slide helps to to visualize that a bit better, what I've done is I've normalized treefold to the fold left. So I've divided one by the other so that if they perform exactly the same, we have a constant 1. If the curve is above the line, that means that the fold left is better. And if they're below the line, that means the treefold is better. And we see that for certain densities, so certain Boolean formulas that have mostly t's or fewer t's, that often the treefold is better, but in some particular cases it's much worse. So my conclusion is that I can't tell you when to use one and when to use the other, because we see this bad result for a density of 2 and also the bad result for a density of 7. So more work needs to be done to try to characterize beforehand what type of approach would be better for your particular problem. In conclusion, the default implementation of fold in Common Lisp and in Scala, which are the only examples that I've experimented with, have some poor performance characteristics in a certain class of problems. Particularly ones, seems to me, where the values that are being accumulated are growing and consuming more and more memory. Particularly rational number arithmetic and BDD related problems. We don't have any, as I said, any way to characterize those problems at the moment. I believe that more research is needed there. And sadly, we have some depressing results for the actual problem that we wanted to solve of generating randomly selected BDDs. I have an implementation of treefold in Scala. It actually is surprisingly difficult to do, to work with every type of collection in the Scala library. I've had many polite arguments with Scala experts about why it's so difficult. And my code is not compatible with Scala 3 because I'm using certain features in my implementation that are going away. I don't know how to fix that. The code is available there, and I'm happy, thrilled to answer anybody's questions or take anyone's challenges.